All right, let's go on a little mathematical ghost hunt today. We're chasing a phantom that lives on the number line. An object so bizarre, so strange, it completely forced mathematicians to rethink the very idea of what size even means.
So let's just jump right into the big central mystery. Is it possible for something to be made of an infinite number of points, but take up literally zero space? It just sounds wrong, doesn't it? It feels like a paradox. Well, spoiler alert, it is, and we're about to build it.
So how do you actually make this ghost? The process itself is surprisingly simple. You start with a solid line, just the segment from 0 to 1. Easy enough. Step 1, you chop out the open middle third. Gone. Now you've got 2 smaller line segments left. So what do? You do it again. You take the middle third out of each of those, and then you do it again and again. You just keep repeating this process forever.
Now, after you've done this an infinite number of times, what's actually left? Well, it's not a line anymore. It's more like a fine powder, this dust of points scattered where the line used to be. And trust me, this dust is holding some pretty wild secrets. But this immediately creates a huge problem. I mean, how in the world do you measure the length of a cloud of dust? Your standard ruler, the one from geometry class, totally useless here. We're going to have to invent a whole new one. Okay, so let's quickly remember how the old ruler works. For any normal, unbroken line from point A to point B, its length is just b minus a, the end minus the beginning. Simple, intuitive, and it works perfectly for solid objects.
But that's the whole issue, right? The Cantor set is not a solid line. It's been completely shattered into an infinite number of disconnected pieces. How on earth do you even begin to measure the length of something like that?
Well, to solve this, mathematicians came up with an absolutely brilliant new tool, the Lebesgue outer measure. The big idea is this. Instead of trying to measure the dust directly, we're going to cover it. We'll use a bunch of tiny, simple intervals to completely blanket all the points. The measure is just the smallest possible total length you can get from all those little covering pieces. It's a super clever workaround for measuring things that seem impossible to measure. So before we point this powerful new ruler at our Cantor set, let's, test it out. Let's try it on some simpler stuff first, just to make sure it gives us sensible answers. We need to collect some clues. And look at that, our first piece of good news. If we use our fancy new measure on just a regular old line segment, we get the exact same answer as our old ruler, its length. Phew, that's a relief. It means our new tool isn't broken. It agrees with the simple stuff.
Okay, next test. What happens if we try to measure a set that has a countable number of points? Now, countable just means you can line them all up and label them. This is the first one, this is the second, the third, and so on, even if the list goes on forever. So what would our new ruler say about the length of a set like that? The thinking here is just beautiful. To measure a countable set, imagine you cover the first point with a tiny little interval. Then you cover the second point with an even tinier one, and the third with one that's tinier still. The trick is you can make these little covering blankets shrink so fast that their total combined length can be squeezed down to be smaller than any number you can think of. And here's the kicker. The only way the total length can be smaller than any positive number you can name is if that length is exactly 0. This is a huge result. It means that any set of points you can count, no matter how many there are, takes up precisely 0 space. All right, we've got our new ruler. We've collected our clues. It is time to go back to the scene of the crime and finally measure our ghost, the Cantor set. So let's think back. We started with a length of 1. After the first cut, the total length left is 2/3. After the next round of cuts, it's 4/9, which is just 2/3 times 2/3. You see the pattern, right? Every single time we chop out those middle thirds, we multiply the total remaining length by 2/3. And when that happens an infinite number of times, that total length gets closer and closer to only one thing: 0. The total length of this infinitely complex Cantor set, according to our powerful new ruler, is exactly 0. It takes up no space at all on the number line. So, case closed, right? We're done. Well, not so fast.
And this is the bombshell. It turns out the Cantor set is uncountable. What in the world does that mean? It means you literally cannot make a list of all the points in it. Unlike those countable sets we saw, no matter how hard you try to label them first, second, third, you will always miss some. In fact, it has just as many points as the original solid line we started with. It's a whole different, bigger, more powerful kind of infinity. So here it is laid out for us.
the paradox in all its glory. Our investigation has found two facts that seem to scream at each other. On one hand, the Cantor set has a length of exactly 0. But on the other hand, it contains an uncountably infinite number of points, as many as the entire solid line from 0 to 1. How can that be?
So, you might be thinking, okay, that's weird, but why does this matter? Is this just some kind of mathematical party trick? Absolutely not. This ghost on the number line, it changed everything. See, discovering things like the Cantor set proved to mathematicians that their intuitions, their gut feelings about things like size and length and infinity were just, well, they were wrong. Or at least they were incomplete. It forced them to build a much stronger, more rigorous foundation for math itself. And that new foundation, it gave birth to whole new areas of study. Our new ruler, this measure theory, led directly to the Lebesgue integral, a way more powerful tool for calculus. It became the bedrock of modern probability theory, giving us a solid way to measure the chances of really complex events. And, of course, it paved the way for fractal geometry, the mind-blowing study of these infinitely complex, self-repeating patterns, just like our Cantor set. So in the end, the Cantor set wasn't really a ghost. It was more like a guide, showing us that reality is way deeper and, frankly, a lot stranger than we ever thought. Which just leaves you wondering, doesn't it? What other impossible things are out there, hiding in plain sight, just waiting for us to invent the right ruler to find them?